In the heart of the refinery stood a 50-meter-tall distillation column. It was originally a precise instrument designed to separate fuels, but in 2005 a series of compounding errors turned it into one of the most tragic industrial accidents in U.S. history. Malfunctioning instrumentation provided false readings. It indicated a liquid level of less than 3 meters, but in reality the liquid inside the column had accumulated to nearly 30 meters, 15 times the normal operating level. When the operators attempted to open the bottom valve to drain the liquid into the storage tank, the catalyst for disaster was accidentally triggered. The scorching hot outgoing liquid passed through a heat exchanger, which conversely instantly superheated the new feedstock entering the tower. The spiking temperature triggered violent boiling and expansion. The runaway liquid quickly filled the entire column and overflowed into the steam lines at the top. The enormous pressure forced 3 emergency safety valves to pop open simultaneously. Subsequently, nearly 200,000 liters of flammable liquid with nowhere to go surged violently like a geyser into the ground-level waste collection drum. However, this drum was wholly incapable of containing such a massive torrent. The liquid instantly overflowed, transforming into a massive flammable vapor cloud that engulfed the nearby area. Just a few meters from the drum, an idling pickup truck inhaled this vapor. The diesel engine began racing uncontrollably; it simply could not be shut off. Finally, a backfire ignited the entire cloud. To understand this accident, we must first clearly grasp how the core distillation column of a refinery works. This line is empty, fragmented in meaning after the previous line. As we know, the crude oil extracted from the ground is a mixture of various gases and liquids. How do we separate them into useful components? The first step in refining is typically distillation. Simply put, crude oil is heated into vapor before being sent into the distillation column. As the vapor rises and cools, it condenses back into liquid. Using the layered trays stacked inside the column, the liquids are easily collected and separated according to their weight. To understand this process, let us assume the crude oil only contains 3 types of gas. The least efficient method would be to gradually reduce the temperature, first lowering the temperature to the boiling point of one gas, which would condense it into a liquid for separation. Then reducing the temperature further to separate the next component. However, in a real distillation column you won't find any refrigeration coils. So how do engineers manage to condense the gas without electricity or cooling? This is thanks to the clever design of the distillation column itself. The temperature within the tower is high at the bottom and low at the top. The bottom is the hottest and the top is the coldest. Crude oil is first sent to a furnace for heating, and most of it becomes vapor that enters the bottom of the tower. Assume the incoming vapor is 400 degrees Celsius and the liquid on the first tray above it is maintained at 370 degrees. Within this temperature field, the actual structures responsible for the separation task are the bubble cap trays inside the tower. You can see that the openings on the trays are fitted with individual bubble caps. The rising vapor is forcibly diverted by the slots on the side of the caps, broken up into fine bubbles that push up into the liquid. This structure maximizes the gas-liquid contact surface area. When the vapor enters the tower and rises upward upon encountering a bubble cap, it must forcefully pass through the lower temperature liquid on the tray. This is where physics takes over. Suppose one component in the gas has a boiling point of 375 degrees. When it clashes into the 370-degree liquid layer, it instantly condenses, remaining on that tray. Conversely, gases with a boiling point below 370 degrees will escape and continue moving up to find the next cooler layer. This process repeats continuously until the crude oil is completely fractionated. However, physical separation is not always perfect. Inevitably, some heavier molecules sneak up to the upper layers. To solve this problem, engineers designed the reflux mechanism, pumping the cooled liquid from the upper layers back down to be reprocessed, ensuring that only the purest components exit the system. Having dealt with the light components, what about the remaining heavy oil residue? Burning it directly would cause scorching. Therefore, engineers use vacuum distillation. The principle is similar to boiling water at high altitudes. By drawing air out of the column, the pressure is lowered, allowing these heavy oils to boil and separate at a lower temperature, extracting the last bit of value from the crude oil. But this presents a startup challenge. Because when the unit is first started, the tower is empty. There is no liquid for the vapor to pass through. So before startup, a preload must be performed. Liquid is artificially pumped in from the top of the tower. Liquid is artificially pumped in from the top of the tower to flow down layer by layer, filling the trays and establishing a liquid seal for gas-liquid contact. Only then can the entire system begin to operate. Finally, let us consider a counterintuitive phenomenon. If you input 159 liters of crude oil, after cracking and processing, it often yields about 170 liters of finished product. This isn't creation ex nihilo, but rather because dense macromolecules are broken down into smaller, lighter molecules, causing a volume expansion. This is the magic of refining. It not only transforms murky black crude oil into gasoline and diesel, but it also grants us an additional volume dividend.